As you said, I'm Abdel, and this is Laurent, and as Martin said, we worked on the native backend for Gambit. The native backend. Why? Why should we bother? Well, like there are many reasons why. One being that the C, the language, imposes code generation constraints which can affect performance, namely when we talk about take calls and continuations, stuff like that. Okay. And another reason that may interest people in using the native backend directly is the possibility of dynamic code execution for like a specific architecture. We got a small example in the talk, the precedent talk by the professor, when he showed an example of assembly code executed. If you remember machine code, like etc. Okay. Now, how does it work? Well, as we all know by now, Gambit uses the Gambit virtual machine as an intermediate representation, like a high level of abstraction for the different backends, be it C or the native backend or the universal backend. Okay. And one other interesting factor is that the development of the native backend has good interoperability with the C backend, meaning that instead of writing the entire system in assembly, like the garbage collection, other OS interface and library procedures, or exception handlers like the stack limit handling and the heap limit handling, these are already written in C, and it would be way too costly to rewrite pretty much everything in assembly. And it allows incremental progress. So as we move and as we add the primitives written in assembly, we can still fall back to the C backend whenever there is a need for it. And that's going to be the second part of the presentation given by Laurent specifically, that bridge part. Okay. Well, we already know by now that the compiler supports many architectures. It's x86, ARM, RISC-V, and many others, PowerPC, etc. But the supported architectures right now by the backend are x86, 32, and 64 bits, ARM 32 bits, and RISC-V 32 and 64 bits. The addition of RISC-V is work I specifically did this summer. Okay. So basically, as we know, GVM has a representation for registers. In the native backend, in the context of the native backend, 5 of them are general purpose registers, with some of them having are typically used for the return address of the current procedure, the return values of procedures. If you remember, like by memory, the GVM outputs that we saw in the previous talk, and for example, another one that's used as a self-register during closure calls, stuff like that. Okay, so we have basically the list for these registers in the GVM and their corresponding registers for the different architectures. So these got mapped, so R0 got mapped to the EDI in the context of x86 32-bit, or R0 in the context of RM, S2 in the context of RISC-V.
Yeah, why sure. Mapping? Like, are there assembly instructions or like speeds or particular operations for by like HP and like 6, 10, and so on?
Repeat that?
Like, why this mapping?
Technically, the mapping is kinda arbitrary to a certain degree.
I disagree.
To a certain degree. To a certain degree.
So they're all general purpose, but certain architectures gives are biased towards certain registers. So, for example, the push operation on x86, it increments the stack pointer. So, if we want to use the push operation, then we need to use the stack pointer in a way that's compatible with our world.
So for example, you can consider like stack pointer. If you come back to the stack pointer example too, so we have, for example, in the RISC-V context, we are using the stack pointer register, not some random register. So yeah.
It really is just because not all registers are equal, and some special instructions operate on specific registers, and sometimes it results in more compactly.
But like, or for another example, you know, another time, like in the RISC-V context, for example, there are many other S register basically for saved arguments or saved values rather, and R2 could have been S11, for example. But it doesn't matter in that context.
Can I add something?
Sure.
In particular for x86 32 bits, there are only 8 registers, and you'll notice that they're all used. And one neat trick is the PS, which is the pointer to the processor state, this structure in memory that has essentially a copy of the GVM registers and so on. And that's in ECX. And ECX on x86 is actually used for shift operations, and when you want to count, you have to put it in CL, and it's the only register where you can do this. So it's convenient to have PS there to sort of use that part of the register and then reload the PS later on. And how that's done is that the lower bits of ECX are actually a constant pattern that we know, which is 8888 hexadecimal. So we can start using it without even saving the PS. We just start using it, and when we want to bring back the old value, we just write 8888 in the lower 16 bits. So it does help to map things intelligently. I don't know about RISC-V because I really don't know that architecture, but for the x86 32 bits, it's really optimized quite a bit.
Okay. So yeah, other registers are obviously used specifically for processor state pointers, stack pointer, stuff like that. Okay. Then I'm going to skip basically over this because at this point we are all masters of the GVM. Okay, so it has multiple instructions, labels, jumps, if jumps, switch for function branches, copy, assignment of values, close for creation, apply, execution of primitives that are in line. Okay. All right. So let's say we have this very basic function. For example, obviously this is, as we already know, the GVM representation. Specifically for this part, it's like the top level specification. So not that much about this part, but the one that's basically named the name of the file hash, so the top level one. So as we see, we have 4 basic blocks. This one, this one, this one, this one. Where, for example, you can see that R2 contains the value 2, R1 contains the value 4 that you pass, jump on in for the interruptions and stack handling, stuff like that. And then the generated assembly is basically quite straightforward. I obviously only limited the output that I showed to like the specific blocks that are represented by like precedently, and not the other stuff that's all around it. But yeah, as you can see, for example, we move. This is basically the value shifted by 2 because of the tagging bits. So that was 2, 4, obviously passed to R2, R1, stuff like that. So it's quite straightforward. And if we move, for example, to the interior of the procedure that I showed, you can remember checking for positives and additioning. Same goes for 4 other blocks. Here we have concretely the addition between R1 and R2. And if obviously you notice, I changed the output, so now it's for the slide, so it's not x86 but rather RISC-V for this case. Okay, and you can see same thing. In this case, we have the addition of the two values that the R1 and R2 completely that are returned, and in the other case, basically returns void. Remember, we had our condition. So if none are positive, obviously it returns the void value. Okay. Okay, all of this is output generated using a verbosity flag during the compilation. We can show a little demo later. Good. Any questions? So yeah, it's a good segue to talk about RISC-V. What is RISC-V? Well, it's an open source hardware instruction set architecture, I say, based obviously, as the name suggests, on the reduced instruction set computer principles. So a very small set of computer instructions. For example, the base ISA for RISC-V contains around 60 instructions, something like that, and 40 pseudo instructions. That's like the very base ISA. And there are a lot of extensions are out there. You'd be surprised to know, for example, that multiplication, anything that's related to multiplication, is in its own separate extension and not on the base ISA. So the base ISA is very, very basic. Typically, it aims for fewer cycle per instructions, and obviously it's a low storage sector, like, for example, RM. It started as a academic research at UC Berkeley, and now it's obviously much bigger than that, managed by the RISC-V Foundation.
There's a group working on GPU instruction set for it.
Yeah, for example, yeah. Obviously,
But they're having trouble communicating with RISC-V because they can't get communications from them unless they sign non-disclosure, which they think is kind of contrary to the idea of open source. But continue.
Okay. We can talk about that later. Sure. Yeah, basically, it's a bunch of companies together that are sponsoring the project for their own usage. Okay. So let's say we want to add a new architecture to the backend, for example. So what are the steps basically to take? The first one being that to add an encoder for the different instructions based on ISA. So basically, within the specs, having different procedures defined to generate the right binary representation for a certain instruction. Alright, same goes for pseudo operations, like assembler directives. For example, the data ones, declaring a double word or something like that. Then, after that, obviously adding the new architecture to the backend code, which requires writing helpers around that. Abstractions, what I mean by abstractions are basically higher level functions to the instructions that we are going to call essentially. So having a add instruction that's obviously mapping the add the proper add instruction for the said architecture, so the x86 add or RISC-V add or something like that, and obviously a lot of primitives to write. Ideally, in the future, that wouldn't be so much the case. So having to write much fewer primitives and much more abstraction around the instructions that are used by the processor, but that's not exactly the case right now. Okay. Obviously, updating parts of the backend to get the proper support for that architecture. That includes also trampoline, code generation, fuck stuff. We might have talks like we will see a little bit in detail in the second part of the talk. And ideally, ideally having Gambit compiled in the target platform, which might require specifying, for example, in the header NDNS. That was the case for RISC-V. And for other architecture, you might even have the need to specify word sizes and stuff like that. Okay. These are actually examples of what you'd find if you look around the files. So this is like an example of the first one, an example of the type primitive implemented as it is for x86, for example. So you have basically an AND, obviously, between the first argument and the mask of the tag, and obviously a shift left on the number of tag bits, and we return the result. So that's directly translated to an AND, a shift left. Another one, for example, this is like for sitting an element in a vector or something like that. So calculating the offset based on the subtype, etc., getting the correct offset and moving data basically in the right section. Okay, benchmarks. So I took, for example, like a typical case Ackermann, the Ackermann function, for example. So as you can see in the C backend, on my laptop, the time is around 3.9 seconds for a few dozen runs in average. And for x86, 64 bits, it's around 3.1. Okay. So decent performance. We could try with Fibonacci maybe later. It's still pretty good. Okay. But it's not always like great performance and everything, since there's still a lot of work to be done. Some is probably not exactly the right term. It's not like, but it's close. Basically, what I did is a loop inside a loop, doing addition many times, and as we can see, the C backend is around 2.9 seconds per average, but the x86 backend is 4.1.
I just want to add that we're comparing the x86 backend with the C backend compiled with GCC. So obviously they have much more resources than we do, and the native backends are still doing native translation from GVM to native code, but still it shows that this GVM code is already pretty optimized. If by doing a native translation, we get performances that are in the same, let's say, order of magnitude.
So your point is like the GCC guys, they have like 500 man years of optimization behind them. You guys just kind of made this, and you're already within like 10% of it.
Yeah,
that's so cool. Yeah.
More like 30.
Is the comparison done with GCC with O3 or? What is the optimization level for the comparison for the CIQ?
That's like the standard level.
O1.
Yeah. I looked around, but they didn't get that much time to look around, but maybe one of the issues is the copy to memory to register to memory. That's happening a bit too much in this case, and that's one of maybe the reasons. But yeah, with more optimization, more time, and more maturity, we'll probably have that around that much. Good. Okay. Now about the current states. So as it is now for x86, around 218 out of the 300 something primitives that are implemented already in C for the not safe declaration, so are basically implemented. So around 56% for x86, mainly everything that's related to fixed nums, type checks, and some memory-related stuff, so allocations, reference setting, stuff like that. Okay, but what's missing? Flow nums, big nums, and some other primitives that I have listed here that are like quite specific. But that all of this is mainly because of lack of time rather than anything else. Okay, but what about the two other architectures? Well, it's more around 25%. But all of this, all of the two other backends are still fully functional thanks to the bridge with the C backend. So technically, they are fully functional, but the implemented primitives for those two other architectures are more around 25%. And that's mainly because it's way too time expensive. It's expensive in resources to actually write 3 versions, let's say, of like the same primitive. So at some point, I just stopped like trying to basically doing copy pasting and changing stuff, and having the need to look into more like generation stuff. So basically, if we have a common mapping and it's already somewhat present for some instructions, for example, but if we have a common mapping to a logical shift to the right, for example, but we can have it mapped, for example, for the x86 to the SHR instruction, and for RM's LSR for RISC-V as parallel, then obviously these primitives can be written once.
Is there any semantic difference between those?
Slight.
Or it's just the bits used to represent the instruction in memory?
It might depend on the instructions.
Yes.
But for the most common ones, obviously it's the representation.
I see. Okay.
So some primitives will still have to be written specifically for the architecture in mind, but most common ones. Okay. So future work, obviously, as I said, refactoring to reduce the duplication between the 3 architectures, add in the rest of the primitives. Ideally, for example, add in support for a 64-bit RM, since we already have 32 bits. Why not have the 64 bits since we have x86 and RISC-V for both? Maybe consider implementations based on like specific extensions if possible. For example, I'm already using, let's say, in a certain instruction pop count, but if, for example, the CPU that's executing the code has support for AVX2, using AVX2 architectures can actually be faster than using the pop count instruction in x86 CPUs, and that's, for example, an optimization that's used in LLVM, for example. Simpler setup to debug the execution for different architectures. So for the development, I had to pretty much use QEMU and emulate the different architectures for the work. It's a bit tedious to a certain degree, but having a nicer setup to debug, use GDB with while emulating these the programs that we are debugging helps obviously during the development process. The last one is like a fun thing that I would personally like to have is like automatic generation of the whole instruction encoder based on the specs rather than having to like manually implement each and every one. Obviously, it can be automated, but it's work. That's about it. Maybe just do a like quick example, for example, with Fibonacci. Let's say.
Prove that this is real.
Yeah, prove that this is real. It's not fake. So I have GCC compiled. 64.
I just want to point out that we're using PPE time, even though they're not defined in the native backends, and this is what I'm going to talk about. So even though they're not defined, we can use them while compiling with the native backends. Yeah, I'm going to say more. Sorry.
So as you can see, the dash, the colon equals wrap, specifying targets. I added the verbosity just so we can get the output for the GVM and the assembly output basically. Should have maybe. Okay, so as you can see, GVM stuff, then obviously the instructions that are related for that. Okay. Executing that. Yeah. So let's try combining that with the C backend instead. C, a bit slower compared, for example, to the x86 backend, but obviously both work.
So you're using only 56%. You only translated 56% of instructions.
Oh, of the primitives.
And you get you expect much more gain if you translate.
Yeah.
Well,
But
not
no.
in this case, just because Fibonacci uses like 5 different primitives, and
This
they're
one is
all
all.
yeah.
It's all different.
I would say that your 56% coverage pretty much covers all of the important ones. I mean, the time critical ones.
so that's about it. Let Laurent talk about that.
So the way you work is the compiler does all the optimizations down to the GVM instructions, and then all you do is manually take what it gives you and you create a procedure to emit assembly code. So there's no optimizations after that, or I misunderstood.
Technically, you can have optimization after
But
that.
for the moment, what are you doing?
Not that much. I mean, like obviously the assembly that's generated tries to be optimal to a certain degree. Like
So you take the GVM code
Yeah.
and you just directly translate, map it to.
I would think that maybe you do some very minor optimizations like knowing that you have a constant and then
and in some examples, for example,
But there's no big optimizations like CPS transformation that's all in the front end.
because you see at the GVM level you might have an instruction that says you do fx plus fixed num plus between n not n, let's say r1 and the constant 1. So the backend will actually see that whole instruction and it sees that there's a constant there. So it could actually, let's say, generate an increment operation, which actually doesn't work because it has to add 4, but just for an example. And there could be a small optimization there, but it's not a very high level optimization.
there was another question. Was it?
Is there a register allocator or you like fixed mapping at the GVM level?
I did that part. So some registers are pre-assigned. Yeah. But sometimes they're not used, so we can use them as free registers. But the register assigner or the register allocator is like users agree the algorithm. So it just picks one at random, puts the value inside, and then we never reuse it.
Because there is like commonly in compilers a lot of optimizations for transform improving the register allocator because you tend to get a problem with register spills like so if you improve the register allocator this might actually improve.
But there's a register allocator in the front end.
So it's in the front end and it gets a fixed mapping so it's allocated at the GVM level.
Yeah, so at the GVM level, there's a register allocation, and because the mapping between GVM registers and the actual machine registers is so close, it's pretty good. It's not perfect, but it's pretty good.
The only register allocation we need to do is when so the GVM may say, oh, add those 2 operands, and the operands may be on the frame. But if you are compiling for ARM or RISC-V, the add instruction only supports registers. So you need to first load the value of the operand 1 inside the register, and then do the same thing for the second operand. So you need to find 2 registers, but I think this is like the most advanced register allocation we're doing in the backend, and it doesn't need to be super complicated. And this may be where GCC beats us. Sometimes we reload the value multiple times.
GCC is very good these days.
Yeah.
In the old days, it used to be horrible.
But I mean, but also the CPUs are optimizing also with out of order and.
Oh yeah, internally, any of those CPUs just kind of like get hundreds of registers and just rename things.
Yeah. But if we force reloads, then like, yeah, CPUs are great, but if we add extra instructions, obviously it's going to be slower. I would also like to add that GCC sometimes pick really specific instructions that we don't even know about. So we don't use them in the native backends. So that's one more reason why sometimes it's faster.
Apparently the people that worked on GCC had machines running for ages, almost running random instructions to see what they did.
I've heard that story.
Yeah. It looked like they would be useful. They checked them out to see if that was just a fluke or not. Yeah, they came up with some amazing bits of code.
My turn?
Okay.
Oh my, yes.
Can I start?
Yes, go ahead.
Okay, so I'm Laurent. I'm going to present the work I did 2 summers ago, where we started working on the native backends, and we did some work on tail calling between code generated by the C backend and the native backends. So obviously, if this is presented here, it goes on Gambit. Gambit has a front end and back end, a C backend, and a universal backend, which can emit like many languages. But the C backend is like the most performant and the most production-ready backend. So this is like our point of comparison, and we think we can do better than the C backend and the GCC, or we thought we could do better. So we started the development of native backends. Here it should be written RISC-V after ARM. I just didn't update my slide. So we started the development of the native backend, and then we realized that it was a lot of work. We had to rewrite all the runtime library and do all the things that were done in the C backend, but now for the native backend, and then maybe multiple times because we target different architectures. And we thought that it would be a really great feature, or it could be really helpful to be able to call code generated by the native backend from C and vice versa. So we defined a term called cross jumps, and this is what the talk will be about. So before showing you how, a few reasons why. So as I've said, the C backend has already everything defined. So for example, the runtime library is written in C and Scheme, and for the native backends, we would need to rewrite the runtime library either completely in Scheme or in a mix of Scheme and assembly. So we would need to rewrite the garbage connector, the OS interface functions, any I/O function, and also because the native backend was still primitive at first, we didn't have access to the complex scheme procedures. So for example, eval, big nums, just because the native backend wasn't able to compile them. And also because not everything was supported by the native backend, being able to call even the simpler primitives that exists in the C backend could be used when like as a crutch for the development of the native backend. Oh, and I wanted to add, it's not written there, but Gambit has debugging functions, and if we could call them from the native backend, then we could already use them while starting the development of the native backend. So here's what we want from the cross jumps. So because we're working on the native backend, because we want better performance, we really want the jumps in the native backend to be simple branch to address instructions. We don't want to use a trampoline. This is just something that exists in the C backend, and it should stay that way. But because we don't want to slow down the existing C code, we don't want to add a check on each function call saying, oh, is this jump going to be a cross jump? So ideally, a C code should just call any function, either defined in C or with the native backend, and it should just transfer the control, and vice versa. And the cost of cross jumps should be similar to a jump using the trampoline, so it shouldn't be overly expensive. So here's how we do it here's how the C backend works. This is going to be a quick presentation because Mark said many things, but one thing he didn't say, he has said the word processor state multiple times, but he never showed you the structure. So here's what it looks like. So the JVM has registers, and we store them into the processor state, and we also store a few pointers. The one that's interesting to us for now is the program counter, because it's used by the trampoline. And also in Scheme, because functions or control points are first class, we need to represent them as memory objects. So we use the label structure to represent them. So as you can see, there's a header, like all objects, and then there's a host field. And the host field is just a pointer to the C function that has the code for that control point. And the trampoline then uses that host field to jump to the correct function. So I'm going to give a simple example using this simple program. It just prints the result of f of 9, and f adds 1 and then squares the result. So we have tail calls and non-tail calls, and here are more host functions, more code. So as we can see, we had three scheme functions, and we have 3 hosts. And inside each host, we have a big switch. The switch just chooses the correct control point to execute. And we see that the cases inside the switch are the basic blocks. So if we just go through the first part of the code, the call to f of 9, we see that we set in R1 the value 9, shifted by 2 because it's a fixed num. Then after f has finished executing, we want to execute print. So we set R0, which is the pointer containing the continuation, to the address of the second control point. So in that case 1, printf. And then we set the program counter to glow f, which is just the address of f. And finally, we can return, and the trampoline will call f on our behalf. Oops. And here's how, and here's what the control points of the program look like. We have 4, 2 in main, 1 in f, 1 in square, and we see what glow f corresponds to. It's just the third element, so plus 1 because it's that. And if we trace through the code quickly, we see that in the top left corner there's a trampoline. So it stops. starts, it calls main, and then the first basic block of main wants to call f, so it returns to the trampoline, and then the trampoline calls f, and then f adds 1, and then it wants to call square, so it returns to the trampoline, which calls square, and then finally we're done, and we want to return to the continuation, so we return to the trampoline, and finally we print and exit. You didn't see the slide. So that was the C backend. In the native backend, we still need to represent the control points as object, but we don't need the trampoline, and because we have access to the machine registers, we use that power to map the GVM registers to specific x86, ARM, or RISC-V registers. And I'm missing something.
The slide you skipped.
No. I can go back if you want. It's just that the trampoline that I have shown you is like the naive trampoline, so we can optimize that. For example, the enable single host is like a big optimization for the trampoline, and it reduces the amount of back and forth between the host functions and the trampoline by just placing everything inside one host function and using gotos instead. So I have showed you how the C backend and the native backend work, but I have not showed you how we do cross jumps. So here's when I do it. So our solution is to define handlers function. We call them bridges, which are used to. Oh yeah, I remember what I wanted to say. It's just that here in the native backend, we don't store the state of the GVM in the same way that the C backend does. So even if we could pass control from one to the other, like they're fundamentally incompatible in the way they store the GVM state. So we would need to like move some state around, which is why we have bridges, because those functions have the only task of intercepting the control when there's a cross jump, and then moving the GVM state to where so for example, if we're calling a C function, then we know that the GVM state is stored in the machine registers, so we take those and we store it in the processor state so that the C code that we're calling can uses those values. Because the native backend does function calls using a simple branch to address instructions, it means that where the pointer to the native label struct points, there needs to be machine code, and because functions defined by the native backend could be called from C, it means that that native label structures need the host field, and in that case we put the address of the toNative bridge in there. So here's an example that's going to be much clearer. Here's what the label structures look like in the case of the native backend. So we see that the reference points directly into machine code. This is the machine code of the procedure. So a call is super simple. You just jump, there's no trampoline, and it's great. And when this is called from C, then the trampoline is going to load the host field, which is the toNative bridge, and call it, and then we can like move the GVM state and then resume the instruction by calling, by jumping directly inside the machine code, as you can see here. And for the native label structures, what we need to do, again, we need to insert executable code where the pointer points. So we did a little trick that results in the execution of the second bridge, and then it's the same trick. We move the GVM state, and then we can resume the execution using the trampoline. And we can do that multiple times, and it supports tail calls. It doesn't create like a stack frame and that. So yeah, it can loop forever, and it's really symmetric. There's no, it's not like a function call where you know that at some point it's going to return to you. You could just finish outside of your control. So here's what the bridges looks like. They're really simple. They're mostly moves. So in the case of the to-native bridge, it's only 18 machine instructions. And the from-native bridge, it's 15 plus an iteration of the trampoline. So it cannot be faster than the trampoline, but we don't know by how much, so we wanted to evaluate that. So we wrote this simple program which just takes the execution time of run, and run just calls the function it takes as argument, the number of times it receives as argument. So in that case, it's going to call deck 100 million times. And the idea to this simple program that does nothing is just to evaluate the overhead of calling deck. So we compile that program entirely using the native backend and entirely using the C backend with the trampoline optimizations and without them. And then, and this is the interesting part, we compile the deck function with the C backend, and we compile the rest with the native backend. So what it means is that every time run calls deck, it's a cross jump. So it calls the two bridges and the trampoline. And by comparing the execution time, we wanted to see what was the difference and how big was the overhead of our solution. And here's what the execution times look like. So to the right, this is the times where we use the bridges and then the trampoline, and we see that they're at worst 1.58 times slower than the trampoline. The second column to the right is our baseline, and we see that when we just stay in native code, it's like 14 times faster than the baseline, which doesn't use the trampoline optimizations. But so yeah, it's even with the trampoline optimizations, which are equivalent to like go-tos or jumps, the native to native times are again faster. So this is like this proves the point where this proves our point, which was that the native backend could be faster because jumps can be made much more efficiently. And for conclusion, all the things we wanted about cross jumps are true. And the use cases in the native backends, they have proven very useful just because we have access to all the existing debugging functions that are compiled with with the C backend. And we hope to not have to write the C primitive, the IO primitives in the native backend and leave them to the C backend just because to save time, because we don't have any limited budget and limited times. And that's it. And here's the slide with and this is like the informal motivation for the native backend. We wanted the first place.
Restless nights.